Never before mankind was so knowledgeable about the fact that we are so ignorant. So we are really on the verge of a big discovery.
Science is going on a journey.
We know 90% of the matter in the universe. We know it exists, but we cannot see it.
Antimatter, S-quarks, neutralinos. The universe is made up of subatomic particles that are hidden out of sight. In order to find these particles, scientists have gone deep underground. Weakly interacting subatomic particles are all that can penetrate down here. But down is not the only place we're looking. We are also looking up. When we look through our telescopes and observe the way stars and galaxies move, we notice something puzzling. The physics of Isaac Newton tells us that the stars at the edge of a galaxy should move much slower than those closer to the galactic core. But observations show that these stars seem to be moving much too fast. Something else must be out there. We can't see it, but it must be there, and there must be lots of it. This invisible mass is called dark matter. Dark because we can't detect it by the radiation it emits. In order to detect dark matter and answer other fundamental questions about our universe, engineers and scientists from all over the world have come together to build this machine, the Alpha Magnetic Spectrometer.
We have 16 countries, more than 600 physicists and from 60 institutes. New York Times said this is the largest international collaboration in space.
Built by institutes and research centres from Europe, Asia and the US, the various components of the AMS have been integrated at CERN, the Centre for European Nuclear Research, and then rigorously tested for space by the engineers at the European Space Agency. When AMS is ready, a space shuttle will blast off from Florida and deliver it to the International Space Station, the ISS, orbiting 400 kilometres above our heads. Unlike many other orbiting spacecraft, only the ISS has enough power and the right infrastructure to sustain the AMS for the years it will spend in space. Before the ISS, an experiment like this would have been impossible. Once in space, the AMS will search for the universe's missing matter by analysing the particles that make up cosmic rays. These rays constantly bombard the Earth. On the surface, our atmosphere blocks most of them before we get a chance to observe them. The AMS will capture these particles by using the largest magnet ever used in space. Ultra-precise detectors will then identify the particles by measuring their mass, charge and energy. Another outcome from the experiment will be invaluable information that will improve ESA's knowledge about the behaviour of magnets in space. In the future, this could be used to build devices to shield astronauts from dangerous cosmic rays during long-term missions to Mars. The visible matter in the universe, such as stars, adds up to less than 5% of the total mass of the universe. The other 95% is made of missing dark matter and energy. In its search for dark matter, the AMS will look for the hypothesized subatomic particle, the neutralino. If neutralinos collide with each other, they're expected to produce an excess of other particles. Nothing else in the universe would leave the same pattern of particles. If AMS detects such a footprint, it will be a good indication that neutralinos do exist, and that dark matter is a sea of them, bathing every galaxy in invisible mass. But dark matter is not the only odd matter the AMS is hoping to detect. It may also detect antimatter, which is even weirder. The father of antimatter was the remarkable English physicist Paul Dirac. His equations predicted something entirely new to science: antiparticles. An antiparticle is a mirror image of a normal particle, except that it has an opposite electric charge. Dirac's work was just theory, but in 1932, Carl Anderson actually detected an anti-electron, the positron. These discoveries won both Anderson and Dirac the Nobel Prize. We think that when the universe was born in the Big Bang, just as much antimatter was created as normal matter. But where is all this antimatter now? The AMS will search for antihelium. Antihelium is almost never created in accidental nuclear collisions in space. If AMS finds antihelium, it will be our strongest indication yet that there might be antimatter worlds in our universe. The AMS will also be looking for an extraordinary form of matter called strangelets. In the 1960s, another great scientific pioneer, Murray Gell-Mann, hypothesized the existence of quarks as one of the fundamental building blocks of matter. We now think that stable matter is made up of two types of quarks called up and down, but it is possible that there could be stable matter made of up, down and S, the strange quark. These particles are called strangelets, and AMS may well detect them. 400 kilometres above the surface of the Earth, in the deep silence above the atmosphere, science now has an opportunity. For the first time, we will be able to observe the universe's most mysterious particles without interference, continuing our quest for the origins and structure of the cosmos. Who knows what we may find?